Okay. So, good afternoon, everyone. I'm Spiros. I'm a research engineer here at the Cyprus Institute. I've been here for the past 2 years, and I've had the chance to work on a couple of consultations that focused on optical character recognition, or OCR. And our job was to explore how these new AI models can improve text extraction and document analysis. So let's first talk about, before we start talking about LLMs, let's look at how OCR tools perform today. So we have tools like AWS, Textract, and Tesseract, which excel at the word recognition and character recognition, but only under ideal conditions, like a clear structure, good resolution, clean printed text. But in real-world scenarios, we rarely have these ideal inputs. Usually documents can be complex, as in like tables, or they can be filled out forms. They can be noisy or low quality scans, some poorly printed, less than 200 dots per inch. They can be handwritten, multilingual, and in these cases, uh, traditional model-based OCR, rule or model-based OCR systems start to fail by misreading or maybe restructuring text. For example, an ID being transcribed by Tesseract leads to this example, which is not useful. So again, so this is what the typical OCR pipeline looks like. You start with an image, a scan, form, or a photo. You feed it into an OCR engine, and the system then will detect all the characters, recognize the word, and output them to you in plain text. So in essence, it's pretty straightforward. It's image in and text out. So an example would be here's a real world example. So this Starbucks receipt, which it's processed by Tesla. So on the surface, it looks fine. The OCR picked up most of the text. It's readable, but it's making some mistakes. For example, V was transcribed into the yen symbol. Change do was changed to change Q, O box from S box, and some other spelling mistakes. And even the date has some format errors, which, I mean, when looking at the receipt as a human, you wouldn't have an issue. Even though it's faded, you wouldn't have an issue understanding what should be there. But for something like Tesseract, this is not the case. And if you have an automated system that depends on accurate transcriptions, these could be critical errors. So this is their key limitation. They can see the text, but they can't always understand. They cannot understand at all what it means or why it's there, for example. So when you integrate an LLM into the OCR pipeline, you essentially have a second step, a second stage, one that depends on language understanding. So the OCR still does what it does by giving you a transcription, but instead of stopping there, the text is passed to an LLM, which can add some contextual understanding before giving you the transcription in the end. So the model can, at this stage, reason about the structure, maybe correct some spelling or formatting errors. For example, okay, knowing that this is a Starbucks receipt and how the cup sizes, for example, are structured, it can fix the EDN symbol into the VT, which I think stands for venti. You have the S box turned into the O box turned correctly into S box, which is a context-aware correction, which, I mean, it's not really a spelling mistake. And it can also fix some of the formatting issues and even correct the spelling. So now that you fix the transcription with the help of an LLM, you can also start doing a lot more with that text. The model doesn't just correct spelling or formatting, it actually understands what different pieces of text represent. For example, it can identify key entities, things like names, dates, total, and it can recognize how these fields relate to one another, like linking the total amount or the amount to a specific item on the receipt or an invoice. And here you can transform plain text into structured data, which is something that you can store, search through, or use in some other pipeline later on. So this step essentially is when the OCR output turns from just raw text into actually useful information. So this is what structured understanding, this is when that structured understanding becomes really useful. Like you, on the left, you have the cleaned up receipt that came out of the LLM beforehand, and you can prompt the model to go one step further and tell it to organize that text into a structured format like a JSON. It identifies what each part of the text means, the merchant, the date, the items purchased, the total, and the payment method. And instead of just a block of plain text, now you have data that's ready to be analyzed, essentially. And depending on the prompt, of course, you can fine tune your output to exactly the way you want it to be. So far, everything we looked at still follows a two-step process. First, you have the OCR that reads the text, and then the LLM that interprets it. But this latest generation of multimodal LLMs, that separation begins to kind of disappear. These models can understand, can see an image, and also understand and transcribe it to you at the same time. So you have essentially recognition and comprehension done jointly by the same model. And because of that, they can also handle more complex layouts like tables and handwritten text more effectively than a traditional OCR system. They can also deal with noisy or low quality scans. And I mean, the biggest shift in this sense is that we no longer have a separate OCR engine and a post-processing step. You directly using one model, transcribe an image and produce structured and meaningful text output. So going back to our first example, suppose you use the Tesseract, the LLM enhanced pipeline. You could not use any model to fix this transcription because it's just fundamentally kind of useless. But using an actual VLLM, which has, we found at least, improved capabilities of text extraction, we can see that you can very easily transcribe this ID and turn it into very usable and actionable data. So we see that these multimodal LLMs are very efficient, are very good at OCR, but we can see how they can also handle information differently. So unlike OCR traditional OCR, which tries to read everything on the page, you can be selective with these models because they can understand the layout and the language, and you can also guide them with prompts. They can tell the difference between a handwritten number and a printed label and a checkbox, which makes them very effective with dealing with complex forms or mixed handwriting, where context and spatial relationship play a big role. For example, let's look at this tax return income form, where we can just use, in this case, I just used the ChatGPT. I gave it this prompt and nothing else, told it to extract the filer's name, social security number, and address. I also told it which format to give it to me, and essentially just gave me a JSON format of all the information that I asked for. And I double checked and it was all correct. Or I could ask it to just give me only the total amounts reported on this form. So it just gave me only the monetary data on this form. It's very important though to talk about what it takes to actually use these models in production. I mean, of course, there's a computational and cost overhead. LLMs require significant hardware resources, especially when dealing with a large database of documents. And even inference can introduce latency. So for large-scale digitalization projects, you need either access to very powerful on-premise infrastructure, or you can rely on commercial or cloud APIs, which of course are quite expensive if you use them over time. The second and major consideration is, of course, the accuracy and the rate of these hallucinations. The quality of the model's output depends very heavily on its size and the data it was trained on. Of course, we found that larger models generally perform better, but again, this ties back to the cost. And of course, sometimes the model can produce text that it looks right to you, but it actually isn't. It's wrong. So for let's say some high stakes document processing like legal documents, maybe financial documents, or something like IDs, you still need, of course, some human validation step or some other automated verification mechanism in place so that these systems are kept in check. So they're going to speak. So to finish, I will talk to you about some of our case studies with using LLMs for document processing. So first case study was with a company here in Cyprus that specialized in offering software solutions, and they contacted us to help them benchmark some models against the Tesseract using their real-world document datasets. So their issues were with poorly scanned text and handwritten samples, and also some layout issues with when processing document forms. We ran this benchmarking and we found, I mean, clear advantages in all of in layout understanding and the way it structured its output, and the accessibility, like cloud versus hosting something yourself. And this also led to a recommendation from us for maybe a hybrid OCR plus LLM pipeline, and also some further testing with proprietary data. Our second case study was with the Ministry of Defense, where our goal was to essentially do a consultation / feasibility study on using self-hosted VLLMs for transcribing a very large database of Greek handwritten manuscripts, which some dated back from decades, from the 60s. So the challenge in this case was handwriting variability. Some documents were quite easy to transcribe, some featured some cursive, and some were featured very heavy cursive, and also some age-related quality degradation on the pages. And in this case, we explored self-hosted visual language models. We explored Gemma, Quen, and Llama Vision, while also testing the performance of a very large model like ChatGPT. we evaluated 105 documents, dividing them into these three difficulty categories: easy, medium, and hard. And you can see the results here. We used the character error rate as our metric for the accuracy, and you can see that most models, even ChatGPT, begins to kind of fail at the medium difficulty. Its accuracy becomes not so good. So we found that all general models have this with Greek data. With English data, this is not the case. And this consultation again concluded that there is a need to fine-tune on domain-specific data. And that's all I have on my end.